So on this one, we're going to use a projectile launcher to launch a sphere, and they want us to figure out about the spring constant of the spring inside, and it can be pushed back to C, B, or A, and the pin holds it in place. So AI and AII are sort of scored together. There's 3 points for both of them. First of all, it says state a law of principle that can be used to determine what the spring constant is. And the best way to answer that is conservation of energy. So that's the easiest way, and there's a couple different ways you can do that. A few people want a different route, which is not ideal, but I'll sort of talk about that as well. A few people said Hooke's law can be used here as well, and I'll sort of talk about all these different routes you can go parallel to each other. So use that principle then to derive an expression. Well, out of that, there's sort of two ways. The easiest way is to say that or it's not any easier, I guess it's about the same, that the spring energy, that potential energy, becomes gravitational potential energy. So this is 1/2 kx squared is mgh, and they want k, so if you did it this way, you would rearrange it, and you would say k is equal to mgh over x squared, and then you would have to multiply it by the 2 up there. So that would be your one route of doing it. Another route you could do is also conservation of energy, and you could say the spring energy goes into kinetic energy. So in this case, we'd say 1/2 kx squared is equal to 1/2 mv squared. And then the halves would cancel, and we'd rearrange to solve for k. So k then would equal mv squared over x squared. And if you did it through Hooke's law, you would have to say that the force is equal to k times x. Now to get the force, as I'll mention later, that's where this route becomes less than ideal here. But you'd have to at least rearrange it because they want to see it that way. So like k is equal to f over x. So 1 point for stating a law that can work, so either one of these, and then another point for sort of translating that into an equation, and then the final point there for writing it in a way that k equals something else. So what about these techniques then to get it and fill out the table? Well, let's say you were going with the method to measure how high it was. You would need the mass, so that would work, and so the symbol for that, let's say, is m, and the equipment could be a scale. You would need the height that it rose to, so a symbol for that could be h or delta y or whatever, and you would need a meter stick or something like that for that way to work. And that is basically it. You would also need to measure the compression distance, and then that we could call x, and you could use the same meter stick for that. So if you want the route of shooting it out, where you would still need the mass, we'd need to get that. We'd still need to get the compression distance. So one thing I'll sort of add on to here is we would need the velocity. And there's a lot of different ways you can do it, but a photo gate might be the easiest. That would be the equipment we would use to get it. That would go over here. So the quantity would be velocity, and the symbol would be v. You could also get the velocity with the meter sticks and a stopwatch, so you could add it in that way. And then the last way, some people want this way with a force probe. So force and the symbol F and a force probe over here. If you say your phone, just be clear, say video analysis software or something like that. Or go into more description, using your phone to take a video with a meter stick in it or something like that. You got to be careful when you go the route of your phone. You can't do it. You just got to be clear. So 1 point for basically listing all the things. Whatever it is you said you were going to measure in this part right here, then you better have equipment to measure it in here, and you get a point for that. So 4 points then for the total of the procedure. 1 point is simply, can you do it in a classroom? So like, deconstruct molecularly the spring, that won't work. So 1 point for something that can be done in the classroom. 1 point for reducing error, so doing it multiple times at each setting. 1 point, because they say, is the spring constant consistent for each different setting there. So you have to be explicit either in this part or the next. 1 point for saying you're going to launch it from A, B, and C. You have to explicitly say that. And then 1 point for just describing the procedure that you did here. So for example, you could say Shoot the ball up, measure the maximum height it reaches, measure the distance you compressed it. Do that multiple times at setting C. Repeat this for setting A. Make sure you get the mass off of a scale. Or shoot the ball horizontally across a table, measure the distance you compressed it. Use photo gates to get the velocity. Do this multiple times at each setting. Repeat for another setting. And then the force situation here, some people try to get the force through an acceleration. You could do that. If you just simply used a force probe to push in the ball and never actually launched it, you will lose a point. So 1 point on this section comes from actually launching the ball. So again, a point for listing your table right, things that you actually need in the table, a point for multiple trials at each setting, a point for saying explicitly you're going to do it at settings A, B, and C, and a point for something that can be plausibly done. You would lose one of those points if you never actually launched the ball. That is, and then in the last part here, describe how you would figure it out to see if they were the same. Well, you solve for the K in each case, so you could compare the Ks in each case. So if you launched it from A, B, and C, see if the Ks are the same. You already have your equations here to find it. You could do a graph. This is a case where you probably wouldn't want to do a graph because you're looking for something to stay the same. So you could say like, oh, you make a graph and it's linear. A lot of people got into changing the mass. Don't need to do anything like that. You just need to see if the Ks are the same. You also want to set, they wanted you to say, and I didn't take off a point for this, something about like, there could be a little variance. It's not like they have to be exactly the same, as long as it's within some sort of range of error that they're equal to each other.